Hello everyone. Today we will study chapter 6, chapter transport layer. We will study these knowledge points: transport service, elements of transport protocol, congestion control, the Internet Transport Protocol, UDP, and TCP, some performance issues. First, we should understand some concepts. The transport layer builds on the network there to provide data transport from a process on the source machine to a process on the destination machine with a desired level of reliability that is independent of the physical networks currently in use. It provides the abstractions that applications need to use the network. Without the transport layer, the whole concept of layered protocols would make little sense. So we will provide an introduction to the transport service. The ultimate goal of the transport layer is to provide efficient, reliable, and cost-effective data transmission service to its users, normally processes in the application layer. To achieve this, the transport layer makes use of the services provided by the network layer. The software and hardware within the transport layer that does the work is called the transport entity. The transport entity can be located in the operating system kernel, in the library package bounding to network applications, in the separate user process, or even on the network interface card. This figure shows the relationship of network layer, transport layer, and the application layer. Our segment in the transport layer, the transmission unit called segment. In the transport layer, there are two types of transport service. The connection-oriented service and connectionless transport service. So the connection-oriented transport service is similar to the connection-oriented network service. So here, transport service is similar to the connection-oriented network service in many ways. In both cases, connections have three phases: establishment, data transfer, and release. Addressing and flow control are also similar in both layers. Furthermore, the connectionless transport service is also very similar to the connectionless network service. So, since the transport layer service is so similar to network layer service, why we need the transport service? So here gives the reason. The transport code runs entirely on the user's machines, but the network layer mostly runs on the routers, which are operated by the carrier, at least for a wide area network. What happens if the network layer offers inadequate services? So, if network layer frequently loses packets, or if routers crash from time to time, routers crash or offer inadequate service. So, the users who have no real control over the network layer, so they cannot solve the problem of poor service by using better routers or putting more error handling in the data link layer, because they don't own the routers. Because they don't own the routers, the user don't own the routers. The users don't own the routers, so have no real control over the network layer. The only possibility is to put on top of the network layer another layer that improves the quality of service. If in a connectionless network, packets are lost or mangled, and the transport entity can detect the problem and compensate for it by using retransmission when error detected. In a sense, the existence of the transport layer makes it possible for the transport service to be more reliable than the online network. Furthermore, the transport primitives can be implemented as calls to the library procedures to make them independent of the network primitives. The network primitives is a kind of system calls, system interface, system library interface. Network service calls may vary considerably from one network to another. Hiding the network service behind a set of transport service primitives ensures that changing the network merely requires replacing one set of library procedures with another one that does the same thing with a different underlying service. To allow users to access the transport service, the transport layer must provide some options to application programs. That is a transport service interface. Transport service interface as a transport primitives. Transport primitives is a kind of function or interface. Function calling function through interface. Each transport service has its own interface. This interface. Here we list some simple transport service. The transport service is similar to network service, but there are also some important differences. So some important difference since they are similar to some extent, but there are also some important differences. The main differences is that network service is intended to model the service offered by real network. Real network can also lost packets, so the network service is generally unreliable. The connection-oriented transport service, in contrast, is reliable. Of course, real networks are not error-free. That means a real network may occur errors. But that is precisely the purpose of transport layer, to provide a reliable service. To provide a reliable service on top of an unreliable network. So the main goal of transport layer is to provide a reliable service on top of an unreliable real network. A second difference between the network service and transport service is whom the services are intended for. The network service is used only by the transport entities. Few users write their own transport entities, and thus fewer users or programs ever see the bare network service. The bare network service. In contrast, many programs see the transport primitives. Okay, we know, for example, here is transport service. Transport service, right? Here is a network service. And this is a bare network service. This is a transport service. This is application layer. Application there, right? So users is here, right? Users is here. User, application, transport layer, network there. So fewer users write their own transport entity. So users usually use the application of the interface of application fewer users write their transport entities, and fewer users ever see the bear. So the users see this transport service and cannot see the bear network service. The transport process is based on the bear network service, but the user only see the application interface or the transport interface. So consequently, the transport service must be convenient and easy to use. So users can calling the interface function of application or the transport but the bear interface cannot. The user does not use the bear interface. That is the meaning of fewer users write their own transport entities, and thus fewer users or programs ever see the bear network service. This table lists some transport service, including listen, connect, send, receive, disconnect, 5 primitives. Listen and connect is used to establish connection. Send and receive is used to send information and receive from the network. Disconnect used to release the connection. So these 5 primitives is the backbone of the transport service. Is truly bare bones. That means these 5 transport service is the basic backbone. It's a basic backbone. So but it gives the essential flavor of what an connection-oriented transport interface has to do. It allows application programs to establish, use, and then release connections, which is sufficient for many applications. Thus, segments are contained in packets. The segment is exchanged by the transport layer, while packets is the transmission unit exchanged by the network layer. In turn, these packets are contained in frames. Frame is the transmission unit exchanged by the data link layer. When a frame arrives, the data link layer processes the frame header. If the destination address matches for the local delivery, passes the content of the frame payload field up to the network entity. The network entity similarly processes the packet header and then passes the contents of the packet payload up to the transport entity. That is the processing. This is the processing of the protocol stack. Figure 3 shows the encapsulation between segment, packet, and frames. Segment encapsulated in the packet. Packet is encapsulated in the frame. That is the relation between the three units. A state diagram for connection establishment and release for these sample primitives is given in figure 4. This figure 4 shows a state diagram. Each transition. H is transition. So, for example, this is a state. The arrow is a transition. Arrow is a transition. So, a state diagram for connection establishment and release for these simple primitives. Each transition is triggered by some event. Each transition is triggered by some event. Here, event includes, for example, an incoming packet, a packet arrival. This is a kind of event, incoming packet, or a primitive executed by the local transport user. A primitive executed by the local transport user. This is a kind of event, or timeout. The third kind is a timeout. So this is the event. The first kind of event is a primitive executed. The second event is packet arrival. The third one is timeout. We denoted by T out, timeout. For simplicity, we assume here that each segment is separately non-acknowledged. We also assume that a symmetric disconnection model is used, with the client going first. Please note that this model is quite unsophisticated. We will look at more realistic models later on when we describe how TCP works. So, based on the formal, the barebone five primitive functions. Here is a state diagram for a simple connection management scan. A simple management scan. It is not a real connection. It is not a real connection management. It is simpler than the real one. Transition labeled in italics are caused by packet arrival. For example, this is a packet arrival. This is a packet arrival, right? Packet arrival. This is a packet arrival. Italics are caused by packet arrival. The solid line, for example, here, the solid line, the right solid lines show the client's state sequence. The dashed lines, for example, the dashed lines, right, show the server's state sequence. So here, the dashed lines is a server sequence. The solid lines shows the client sequence. So the network, one end is a server, one end is a client. They have its in separate. This is a separate state diagrams, but they are drawn in the same figure. Now, about socket is an important concept, especially Berkeley sockets. Sockets were first released as part of the Berkeley Unix BSD software distribution in 1983. They quickly became popular. The primitives are now widely used for Internet programming on many application systems, especially Unix-based systems. Unix-based systems, for example, Linux, 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 or Mac. Linux usually Ubuntu, Ubuntu, Linux, Mandrake, or Sun Solaris systems. There is a socket-style API for Windows called WinSock. So usually, if you are using Windows system, then when we want to design networking applications, we should use WinSock. It is a kind of socket-style API. Then we can use them to design networking application. Usually, the socket's function include this socket primitive. This is a primitive using socket to create a new communication endpoint. In the experiment 4, this is the last experiment. We will design networking application. It is more complex than experiment 3. In experiment 3, in this morning, the experiment is so simple. We should only open servers, web server, FTP server, etc. And we can design a simple homepage using a hypertext markup language, HTML, based on the examples. It's very simple. But for experiment 4, the last experiment, we should use these primitives, use these functions to design networking application to make 2 machines to communicate with each other. So the last experiment is some complex, some complicated. Because we should use these primitives: socket, bind, listen, accept, connect, send, receive, close, to design networking application. So socket is a function to create a new connection endpoint. Create a new connection, a new communication endpoint. Example, this is an endpoint. This is an endpoint. This is A. This is B. Then this is a transport layer, right? This is a transport layer. Then we can use these endpoints, use the primitives to create connection between the 2 endpoints. Then A can send data, then B can send. So is can use the socket to create the connection between A and B. Bind, the bind primitives use bind to associate a local address with a socket. So when we create a new socket object, we should set some arguments, some parameters, includes local address and ports with the socket. That is a binding. Bind address and port with the socket object. The third is listen. Listen means when the server end setup, it will turn to the listening state. Listening state means waiting for the connection from client, right? Listening connection request from client endpoint. This is listen. So listen is announced willingness to accept connection. Give a key size. The fourth primitive is accept. Accept is also the primitives at server end and passively establish incoming connection. An incoming connection request from client. This is from client, and accept by servers, right? This is a server, right? This is a server client. Is a server client because incoming connection request comes from client, right? Connect request is from client, right? Connect actively attempt to establish a connection. Receive, send and receive for information transmission. This is for connection, right? This is for data transmission. Send some data over the connection, receive some data from the connection. So when the connection is established, then the two ends can exchange information based on the connection. After finishing the transmission, the connection will be closed. It means release the connection. That is the socket. This is the socket primitives for TCP. Okay. Now I want to. Okay, let's have a rest for 10 minutes. Let's have a rest for 10 minutes. Have a rest for 10 minutes. Okay. So I want to zoom in this code. So so let's have a rest for 10 minutes. Okay, let's continue. Just now, we have introduced the sockets. Now, this slide shows a networking code using sockets. This page contains a client. Page contains a client. This is a client, right? A client program. A client program that can request a file. Request a file from the server program on the next page. So this page contains client programs and the server programs on the next page. So the server is here. This is a server code, right? This is a client code. So So let's look at the networking application. This is some include types socket.h, in.h, netdb.h, etc. Here defines some const server port, for example, 12,345. Buffer size 4,096. This can define. Here is main, right? Here is main function. It is C or C++, right? This is a C. This is a C or C++ program. Int define CS bytes. Here and char define buffer. Define a buffer is the area of character. And struct host ent is a pointer. H is a pointer H. This host ent is a data type probably defined in this header file. And socket address in probably defined in these files. Then, okay, this is defined some variables. If the argument count is not 3, then then output an error message. Then by calling this function getHostByName to look up host's IP, Usually, how can we know the IP address of your machine? Now, you can click, you can click this. Okay. Oh, you can start up the CMD, right? Then you can input config, ipconfig /all, or then output the information of your ipconfig information. For example, your network interface card, a MAC address, your MAC address. This is the wired. This is a wired. Now, here, wireless LAN, Realtek wireless. This is a MAC address. This is a MAC address of your wireless LAN interface. And IPv4 address is this. So this is the IP address. This is the IP address of my computer. So if you want to know what's the IP address of your system, usually you should input this command and check this line, IPv4 is 4. This is your address. But how can a program to determine the IP address of a certain machine? Of a certain machine. So here, this function getHostByName make the program to know the IP address of the machine it runs on. So this is the function to know the IP address, to look up host's IP address. This is the getHostByName. And usually we know the Windows etc. Sorry. etc. I will check etc. Okay, the host pause. Et. Oh, okay. I will not to find the host. The next time I will show the local ENS configuration. Now, okay, this function socket. This is socket. Do you know the socket? This is the socket. Socket here. Socket, right? It's a socket to create a new communication endpoint. Use socket to create a new communication. So that is why I will illustrate 9 by 9. Use the socket function. This function is a kind of primitives. By calling the socket function to create a communication endpoint in the client server, in the client endpoint. And this function has 3 parameters. Protocol family, PF here, PF means protocol family of internet, INET means protocol family of internet, and use stream, This stream means we use TCP. So this is stream and TCP. So this is create endpoint. Then is it successful to create endpoint? If S less than 0, then it's error occurs. So fatal socket. This fatal means output a message to inform an error occurs. Cannot create socket. set. Now, if S is larger or equal 0, then it is successful to create endpoint, right? Then we'll set some arguments. set here channel here, right? Here channel is a socket address, says host IP addresses. So set 0 size of, that is, for example, we will save an IP address in this bytes, in this array of bytes. Then we cleared at first. And set all zeros in the memory area. So set this number of zeros of bytes, size of channel. This is a channel, and the size of, this is size of, and set all zero with 0. So this is set. Channel dot SIN family set with AFINET. Here AF means address family. Address family of internet means here we will use IPv4. Here we will use IPv4, means that is what that means. MEM copy, because this is a structure type, so we should use MEM copy. Channel.sin address.s address. Here, copy this. Since here we get H, right? The host's IP address. So, and net S address equals H host. This is nans, the number of bytes. Then H2NS hosts to the network sequence, host sequence. Since the host sequence is different from the network sequence, so by calling this function, return the host sequence to the network sequence for integer types. Then, now, at this point, the connection is ready. It's ready. Then, by calling the C equals C connect, for example, this connect, right? The connect actively attempt to establish a connection by the client endpoint, right? By the client endpoint. Connect. So, connect actively send connect request. If C is less than 0, then output a fatal message. Connect failed. If C larger or equals 0, then connection established successful. Now connection is now at this point, connection is established successful, right? If not successful, then fatal then exist at this point, right? So since at this point the connection isn't successfully established, then how can we download file from the server? So if you want to get some file from the server, you should tell what's the file name. So send file name send file name. So write as argument v2 s. What is the s? S is the socket, right? S is the socket. That means send this value with the socket S. That means set the file name, send the file name to the server. The argument v, that means, for example, this is Windows, right? Prompt is this. Then we input here, input some argument. This is a program name, right? This is the program name. This is the server address. This is the file name. So the third one is argv2. argv2 here. This is 0, this is 1, this is 2. So argv2 is the third argument, right? So send the file name. Then go get the file and write it to the standard output. Write here means send messages to the network with the channel. Then while 1, it is a loop. Right? Loop. Read here, read means receive data from the socket S. From the socket S. From the socket S. If the bytes equal or less or equal 0, then exist. Right. Okay. This is a client. It's a client. So then we will briefly look at the server. An example of socket programming, an internet file server. It is a very simple example for internet server. It is not an actual FTP server code. So this is a server code. So usually networking application, we need a client. We need a client program. We need a client program and a server program, right? We need a client program running in machine A and a server program running in another machine. Then server end start up at first, running and waiting. Then that means at first we should design a server code. Then we should design a client code and run server code at one machine, then run a client code at another machine. Then client code, client program send request to the server. Server then reply messages to the client. Do you understand? So we should design a server end and a client end and run the server end in one machine at first. Then run client end in another machine or in the same machine. Then client end send the request to the server. Server reply to the request. That is what the networking application do. Networking applications do. Now, we check the server code. This is including some header files, define some constant variables. Then this is the main function of server code. And here the integer int SBLFDSA bytes arm. Here arm is set 1. Here is a buffer and there is a channel. Then build address structures to bind to socket. Here bind address. This is a command. Right? Command. Bind address structure to bind to the socket. Then passive open, wait for connection is for server code. This is a server code, right? This is a server code. So create a socket by socket primitives. And bind, here is a bind and listen. Listen, as create, bind, listen. That is passive open, wait for connection. Wait for connection. That is listen, right? This is a listen. The socket now at this point, socket is now set up and bound. Wait for connection and process it. While one means nope, turn by turn, then accept, here accept, right? Socket bind, listen, accept. What is the accept? Accept here, right? Accept. Passively establish incoming connection, right? Passively, passively, not actively, passively. Server usually passively establish incoming connection. So now let's continue. Accept. Then read. Read means read the file name from socket. Read the file name from the socket. Here accept passive the block for connection request. Block. What is the block? Block means when the code running to this point, if there is no request, the program blocked. The blocked. It is not doesn't stop or exist, but blocked here. This is a block. It is a block is an important concept in the operating system. It is an important concept in the operating system. There is a block. Okay. If a request, then the code continues. Then read file name from socket. Then get and return the file. Since the file name received and saved to the buffer, then open the file with the file name in the buffer. So here open file to be sent back. Then create. FD means FD is a file it is a variable name. File description. Description. Then here is a while one means it is a nope. It's a nope here. Read from file. Read from file. Right, read from file. Then write bytes to the socket. Then send back the file according to the file name. Then close the file. Close the file. Close the connection. Here close. So here close the connection. Right? Closed. So it is a good example. To learn the primitives. So if you compile the code in the Linux platform, then it's okay. But I think it cannot compiled in the Windows platform. If you are using the Windows platform, probably you need install CYGWin. You need CYGWin. You need the CYGWin. So in the CYGWin, you should install CYGWin in your Windows. Then you can use the command in the Windows platform, right? In the Windows platform. For example, this is a Windows system, but I have installed CYGWin, so I can use ls, the pwd, this etc. And I can use GCC. I can use GCC command, and I can use config. Sorry, the Chinese character cannot be displayed. So now let's continue. So I have illustrated in detail about the client and server code because we will design some networking code in the next experiment. Now let's continue the transport service is implemented by a transport protocol used between the two transport entities. In some ways, transport protocol resemble the data link protocols we studied in detail in Chapter 3. Both have to deal with error control, sequencing, flow control, among other issues. However, significant differences between the two also exist. At the data link layer, two routers communicate directly via a physical channel, whether wired or wireless, whereas at the transport layer, this physical channel is replaced by the entire network. This difference has many important implications for the protocols. These differences are due to major dissimilarities right, between the environments in which the two protocols operate. Figure 7, here subfigure A shows the environment of data link there. The data link there. This is a physical communication channel here. Subfigure B shows the environment of transport layer. Transport layer, that means this is a network. We don't know how many hops, how many routers, how many links between the two ends. So which one is more complex? That is, the environment of the transport layer is more complex. It's more complex. Complicated, right? Okay, that's all. So much for today. That's all. Thank you. Bye.